Welcome to Mindcast. I'm your host, Will, and today we're diving into one of the most fascinating stories in modern technology. It's a story about how the pursuit of one seemingly simple goal, organizing the world's information through web search, accidentally built the engine that's now bringing us to the brink of artificial general intelligence. This isn't the story you'd expect. It's not about brilliant scientists methodically working toward AGI. Instead, it's about how Google's quest to index web pages inadvertently constructed the very infrastructure and data sets that would later power ChatGPT, GPT-4, and the current AI revolution. It's a tale of unintended consequences on a planetary scale, and it starts in the summer of 1956 with a group of researchers who got intelligence completely wrong. Picture this. It's 1956, and a small group of brilliant mathematicians and scientists gather at Dartmouth College for what would become known as the Constitutional Convention of AI. John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, these weren't just any researchers. These were some of the brightest minds of their generation. And they made a bold declaration that would shake AI research for the next 30 years. They believed that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. This was the birth of what we now call the Dartmouth conjecture, the idea that intelligence is basically symbol manipulation following logical rules. Think of it like an incredibly sophisticated calculator, but instead of numbers, it manipulates concepts and words according to programmed rules.
This symbolic approach, later dubbed good old-fashioned AI, actually worked pretty well in controlled environments. Programs could prove mathematical theorems and have basic conversations about simple worlds filled with colored blocks. The early optimism was infectious. The Dartmouth organizers literally thought they could make significant progress toward human-level AI in a single summer. But here's where the story takes its first dramatic turn. The real world, it turns out, is nothing like a controlled laboratory environment. It's messy, ambiguous, and governed by an almost infinite web of unstated common-sense knowledge. How do you program a rule for knowing that ice is cold, or that people don't usually wear shoes on their hands, or that a bank can be a financial institution or the side of a river depending on context? The symbolic systems were incredibly brittle. They worked perfectly until they encountered something they weren't explicitly programmed to handle, and then they failed catastrophically.
By the 1970s, this brittleness ran headlong into a fundamental mathematical barrier called combinatorial explosion. As you try to add more rules to capture real-world complexity, the number of possible interactions between those rules grows exponentially. Your system becomes computationally paralyzed, unable to make decisions in reasonable time. In 1973, Sir James Lighthill delivered what became known as the Lighthill Report to the UK Parliament, and it was devastating. He criticized AI for its grandiose objectives and utter failure to achieve them. The report led to the complete dismantling of AI research in the UK. In the US, funding dried up as agencies lost patience with over-promising researchers. This was the beginning of the first AI winter, a period of stagnation that would last for decades. But here's the fascinating part. While academic AI research was languishing in this winter, something completely different was happening in the commercial world that would eventually change everything. While AI researchers were struggling with the combinatorial curse, the World Wide Web exploded onto the scene in the 1990s. Suddenly, there was this chaotic, unstructured, exponentially expanding network of information, and companies were racing to organize it. Google wasn't trying to build artificial intelligence. They just wanted to help people find relevant web pages. But the scale of this problem was unlike anything that had ever been attempted. We're talking about indexing and searching through billions of web pages, processing millions of queries per day, and doing it all in real time. No existing technology could handle this, so Google had to invent everything from scratch. And in doing so, they accidentally solved the two biggest problems that had been holding back a completely different approach to AI, an approach based on learning patterns from massive amounts of data rather than programming explicit rules.
First, Google built a planetary-scale computing infrastructure. They created the Google File System to reliably store petabytes of data across thousands of commodity servers. They developed MapReduce, a framework that could process enormous datasets in parallel across those thousands of machines. They built Bigtable for fast, flexible data management. Together, these technologies form the backbone of a new kind of computer, not a single powerful machine, but a vast network of interconnected processors working in concert. This was the compute infrastructure that future AI would desperately need. Second, and perhaps even more importantly, Google was creating the largest dataset in human history. Every search query paired with the links people actually clicked became a training example, a question, and a relevant answer. The entire internet became an implicitly labeled dataset of human knowledge and preferences, continuously updated and refined. By the 2010s, Google was processing over 8.5 billion searches per day. That's not just infrastructure. That's the fuel that would power the next generation of AI.
But there was still a missing piece. The hardware was there, the data was there, but the algorithms weren't quite right yet. The dominant approaches for processing language, recurrent neural networks, and long short-term memory networks had a fundamental limitation. They had to process text sequentially, word by word, updating their internal memory at each step. This meant you couldn't parallelize the computation within a single training example, creating a severe bottleneck that limited the scale of models you could train. It was like having a massive parallel supercomputer but being forced to use only one processor at a time. Then came 2017, and a team at Google published a paper with a deceptively simple title, "Attention is all you need." This paper introduced the transformer architecture, and it was the missing algorithmic piece that would finally unlock the potential of all that search-air infrastructure.
The core innovation of the transformer was something called self-attention. Instead of processing words sequentially, self-attention allows a model to look at all the words in a sentence simultaneously and determine which relationships are most important for understanding each word's meaning. It creates a fully connected network where every word can directly attend to every other word, regardless of their distance from each other. But here's the crucial part. Because it eliminates those sequential dependencies, the transformer allows for massive parallelization. All those complex calculations for every word in a sequence can be performed at the same time, making it a perfect fit for the parallel processing capabilities of modern hardware like GPUs and TPUs. The transformer wasn't just a better algorithm, it was the right algorithm for the hardware paradigm that Google had built. It was like finally having software that could run at full speed on the world's most powerful distributed computer.
Once you had the transformer architecture running on Google's massive infrastructure and trained on their enormous datasets, something remarkable happened. Researchers discovered that AI improvement follows predictable mathematical laws. In 2020, OpenAI published their landmark Scaling Laws paper, showing that a language model's performance improves smoothly and predictably as a power law when you increase three factors: the number of model parameters, the size of the training dataset, and the amount of training computation. This held true over more than 7 orders of magnitude. It meant that simply making models bigger, feeding them more data, and training them for longer would reliably yield better results. The era of bigger is better had a mathematical foundation. This was refined in 2022 when DeepMind trained Chinchilla, a 70 billion parameter model, on 1.4 trillion tokens of text. Despite being 4 times smaller than their previous model, Chinchilla outperformed it because it was trained on much more data. The lesson was clear. For optimal performance, you need to scale both model size and training data in roughly equal proportions.
But here's where the story gets really fascinating and a bit unsettling. While researchers could predict smooth improvements in basic metrics, they started noticing something else entirely. As models crossed certain scale thresholds, they didn't just get incrementally better, they suddenly acquired entirely new capabilities that were absent in smaller models. Google researchers called these emergent abilities. For example, the ability to solve multi-step math problems, answer college-level exam questions, or follow complex instructions only emerged once models reached a certain size. Below that threshold, performance was essentially random. Above it, performance jumped dramatically. One particularly striking example is chain-of-thought prompting. If you ask a small model to think step by step before answering a question, nothing happens. But ask a large enough model to do the same thing, and its reasoning performance improves dramatically. The models were developing new capabilities that couldn't be predicted by extrapolating from smaller versions.
This creates a profound paradox at the heart of modern AI development. We have predictable scaling laws that tell us exactly how much compute and data we need to improve performance, but we can't predict what new abilities will emerge when we reach certain scales. We're climbing a smooth, quantifiable hill, but we have no idea when we'll suddenly crest a ridge and find ourselves in completely uncharted territory. This brings us to the current moment and one of the most contentious debates in AI. In 2023, a team of Microsoft researchers published a paper with a provocative title, Sparks of Artificial General Intelligence, Early Experiments with GPT-4. Their claim was extraordinary. The GPT-4 represented an early, incomplete version of artificial general intelligence. They argued that the breadth and depth of GPT-4's capabilities across mathematics, coding, medicine, law, and psychology demonstrated a more general form of intelligence than had ever been seen in an AI system.
The evidence they presented was compelling. GPT-4 could generate complex code, pass professional qualifying exams, and even demonstrated theory of mind, the ability to reason about other people's mental states. These weren't just feats of memorization, they appeared to be demonstrations of genuine reasoning capability. But this claim has sparked fierce debate in the AI community. Some researchers see models like GPT-4 as emerging AGI, while others argue they're sophisticated mimics that lack true understanding. Surveys of AI researchers show wildly different predictions for when AGI might arrive, from the late 2020s to many decades from now, or possibly never. This uncertainty highlights a fundamental problem. We've become incredibly good at engineering systems that exhibit intelligent behavior, but we don't really understand how that intelligence works internally. The models are largely black boxes. We can observe their external behavior, but we can't peek inside to understand their internal reasoning processes. This opacity creates serious challenges and risks. The alignment problem, ensuring that an AGI's goals align with human values, becomes nearly impossible to solve if we can't inspect or understand the system's internal motivations. There are concerns about mass unemployment as AI automates cognitive labor, the perpetuation of biases encoded in training data, and the ultimate existential risk of losing control of a superintelligent system. Many leading AI experts believe this should be treated as a global priority on par with climate change or nuclear threats. We're in the peculiar position of scaling a technology whose ultimate capabilities and internal motivations are fundamentally unknown to us. We're building systems more capable than we can fully comprehend or control. And this brings us full circle to the central irony of our story. The journey toward artificial general intelligence began with the Dartmouth Conference's dream of programming intelligence through explicit logical rules, a top-down approach where humans would carefully craft every aspect of an AI system's behavior. That approach failed spectacularly because the real world proved too complex to capture in handwritten rules. The resurgence came from the opposite direction, a bottom-up approach where systems learn patterns from vast amounts of data. But this learning required two things that the symbolic AI era couldn't provide: massive computational resources and enormous data sets. Neither was built with AI in mind. Google's planetary scale infrastructure was built to index web pages. The massive data sets were created as a byproduct of people searching for information online. The transformer architecture was designed to solve machine translation problems, not to create artificial general intelligence. Yet when these three elements came together, the search-era infrastructure, the web-scale datasets, and the transformer architecture,
They created something that neither Google's engineers nor AI researchers had explicitly set out to build. Systems that many of the world's leading experts believe show genuine sparks of artificial general intelligence. It's a perfect example of what evolutionary biologists call exaptation, when a trait that evolved for one purpose becomes the foundation for something completely different and far more significant. Google's search engine became the engine for AGI. What started as a commercial imperative to organize the world's information has brought us to the threshold of one of humanity's most transformative and potentially dangerous technological achievements. The Unforeseen engine, built to index the past, is now rapidly shaping the future.
So what does this mean for us? The technical challenges of building more capable AI systems are being solved by the relentless logic of scaling. More compute, more data, bigger models. But the real frontiers now are scientific, ethical, and societal. We need to understand how these systems work internally. We need to figure out how to align their goals with human values. We need to manage the societal disruption they'll cause. And we need to do all of this while the technology continues to advance at breakneck speed. The story that began with a simple search query, how do I find relevant information on the web, now concludes with some of the most profound questions facing humanity. What is intelligence? Can we create minds more powerful than our own? And if we do, can we ensure they remain aligned with our values and under our control? The path from web search to artificial general intelligence is a reminder that the most transformative technologies often arise not from direct pursuit, but as unexpected consequences of solving seemingly unrelated problems. As we stand on the threshold of what might be artificial general intelligence, we're facing both unprecedented opportunities and existential risks. The Unforeseen engine that began with the simple goal of indexing web pages has become one of the most powerful forces shaping our future. Where it ultimately takes us remains an open question, one that will define the trajectory of human civilization for generations to come. Thanks for joining me on Mindcast. I'm Will, and until next time, keep questioning, keep learning, and keep marveling at the extraordinary unintended consequences of human ingenuity.